Good morning, everyone. So welcome to this lovely conference. Welcome to pyData Berlin 2015. So just a couple of quick words from the organizers here to get you all started. So welcome, everyone. So the first thing I'd like to say is it's all about the community. So this conference wouldn't really be possible without all of you in this crowd. I'm really happy you all turned up. So I think we have, in fact, sold out entirely. So there are 0 tickets left. Well done on that. Regarding the wireless, so there is wireless. There's information about the wireless sort of spread throughout the room. Then the toilets are on the 1st and the 3rd floor. The schedule is online, so we decided not to print any schedules because it's online and we didn't really want to waste that much paper. Also, you can tweet using the hashtag pyDataBerlin. There's also an account here, pyDataBerlin, on Twitter, and you can follow that for updates. So if there's going to be any updates during the day, I'll try to post them to that account. So this room is called the Inno Space, and it's the right-hand side of the schedule. So if you have a look at the schedule, all of the talks on the right-hand side here are going to be in this room. And then there's another room across the hall, which is called the Event Space. And that's going to be for the tutorials. Then there's going to be a social event with the BBQ tonight. So that's going to be outside. I've been told the weather is going to be really nice. So that's going to be downstairs and in front of Beta House. Also, please avoid touching the video equipment. So there's 2 cameras in this room and 1 camera next door, and they're a little bit fragile. So try to avoid sort of touching them or connecting your laptops to the sockets near them. If the cameras turn off for whatever reason, it means that the streams will break down. Which brings me to the next point. So there are streams. So I think I am actually streaming this right now. Yeah, maybe not. So the streams are here. Yeah, this is the stream. So I can see myself talking here with a little bit of lag. Yeah, jolly good. So what else? So this is on streaming.media.ccc.de. So there's basically 2 streams available. We're hoping that they're going to be stable throughout the day, but as these things go, they might break down. Let's hope they stay up. So the 2 last points are there's going to be lightning talks this evening before the social event. There's a flip chart at the other side of the room near the registration desk. If you want to give a lightning talk this evening, please do write it down on the flip chart. It's on a first-come, first-served basis. So the quicker you sign up, the more likely you are to be able to hold your lightning talk. Are there any questions? Okay, no questions. Then it's my pleasure to introduce Matthew Rocklin. He's an open source developer. He works for Continuum. Speaking of Continuum, we'd like to thank our sponsors. So all of our sponsors are listed over here: Continuum Analytics, Blue Yonder, the Python Softwareverband e.V., iQuant, Python Academy, the Unbelievable Machine Company, and Plotly, and of course the CCC Video Operating Center for doing these amazing videos and recordings and bringing all the equipment and staying here till 1 o'clock in the morning to get everything set up yesterday. So thank you very much to all those people. So Matthew is an open source developer, and he works on some really amazing Python tools. Amongst those are SymPy, so he's contributed to SymPy. He's also recently done some work on a tool called Dask, which is sort of focuses on parallelism and arrays, and that's what he's going to be talking about today. So give it up for Matt.
How much time do I have? When should I finish by?
So I think you have 50 minutes.
Okay.
Let me just check the schedule.
My time's running out.
So go ahead. Yeah,
okay.
Till 10:20, so 50 minutes.
Great. So hi, everyone. My name is Matthew Rocklin. I work for Continuum. For those who don't know, Continuum is a for-profit company sort of embedded in the open source pyData ecosystem. So they make Anaconda, as most people know about them. Do consulting. They also apply for government grants. And so all the work that I'm going to talk about today is sort of open source grant-funded work. Continuum sort of just generally tries to make the pyData ecosystem better. The incentives are sort of in the right place for that. So I usually talk about Dask arrays. Dask is a project that sort of grew out of Blaze, this other big project. But I'm sort of think the schedule says Blaze. Today's we talk about Dask. Because it's the first talk, I'm also going to talk sort of more generally, not just about my library, but about parallelism in general in pyData, and sort of the state of that, why it's a little bit wonky, and maybe why it's going to be better in the future. So there's sort of standard library talk, and then coupled with more general talk. So again, there's sort of my talk is about Dask array, which is a multi-core, meaning it uses all of your cores. Out of core means it uses data sets that are larger than your memory. NumPy clone, so it sort of looks and feels like NumPy, but is maybe bigger. And then surrounding that, we'll talk about parallelism, sort of the core of Dask and how it can be used maybe to do more parallelism, and then the GIL, and sort of why we care about that. So that's what we're talking about today. It's a long talk, so questions at various times are really welcome. So if you have a question, please flag me down and say something. Okay, so when we talk about parallelism, I'm going to sort of classify data sets into three sizes. One is sort of the gigabyte size, or less. This fits in memory. You generally need one core. It runs in sort of seconds. Most data fits here. This is what works on your laptop. There's sort of the terabyte size. This you can conceivably use on a laptop. This sort of fits in your hard drive, but it's sort of inconvenient. And I would say that if maybe 95% of data sets fit in a gigabyte, 99% of data sets fit in a terabyte. I have found the sort of big, heavy workstation to be the sort of ideal computing environment in that case. But you could also go to Spark clusters or whatnot. Then there's sort of the petabyte scale. And if you're Google or handle all of the tweets for the world every day, you're sort of the petabyte scale. I'm mostly going to focus today on problems that are in this sort of terabyte range. If you're in the gigabyte range, and I suspect that almost everybody is in that range, you can ignore everything I'm going to say. If you're in the petabyte range, I have nothing to give to you. You need to use Hadoop, or HPC, or Spark, or whatever. So again, I'm sort of just talking about this terabyte range, which is sort of a very interesting space. A lot of sort of fun data sets are just sort of entering that space. Okay, so we have this sort of pyData conference. It's built off of this software stack. My job at Continuum is to sort of think about that software stack and ways to make it faster or easier to use. And so it's sort of interesting to think about the whole software ecosystem as a unit rather than a particular library. And this whole ecosystem is really defined by the libraries that build off of NumPy and pandas, this n-dimensional array and this sort of in-memory table. And so here's my sort of image of that ecosystem. So at the very bottom, we have languages like C and Fortran and Python, right? And ignore the colors for now. We'll get back to that in a bit. And in C and Fortran, we have libraries like BLAS and LAPACK, these sort of very hardcore libraries that are written for speed and are just amazing. On top of that, we have NumPy. On top of that, we build lots of library code. SciPy, all the scikit image, all the scikit things, scikit image, scikit learn. There's visualization, there's pandas, etc. And again, sort of on top of all of these libraries, we've built many other libraries. And the interesting thing that comes out is that all of these libraries can now talk to each other because they all use the same core data structures. Okay? So it's really fascinating that we can store data in HDF5 or PyTables or bcalls or whatever, load it into memory, and then do stats models or scikit-learn or scikit-image, and then visualize it with matplotlib or bokeh or seaborn. And we can change out any of those and not have to have any coordination between those libraries. So the developers of those libraries talk to each other a little bit, but not too much. They didn't all have to agree ahead of time. They all agreed just to use NumPy arrays. And that agreement sort of allows you to select and choose whatever you want. So there's a lot of benefits to basing the entire ecosystem off of a couple of core data structures. Okay. But NumPy is old. So if you go on to, this is the SciPy Git repository. So the SciPy and NumPy are older than this. It's just the first couple commits inside those repositories. And so this is work by Eric Jones, Enthought, and Travis Oliphant, now Continuum. These are the first couple commits. This is the date here is relevant, right? It's 2001. And you should think, what did your computer look like in 2001? What did your problems look like in 2001? And that was where NumPy was designed, right? And things have changed since then. So NumPy and pandas have some pretty striking limitations. Mostly, what we're talking about today is they're both single-threaded, mostly. So they're sort of designed to use one thread, one corridor of your machine. And they are sort of in-memory data structures. Okay, so they're not designed to be larger than what fits comfortably in RAM. There are other problems, like variable length strings and poor missing data support, which in 2001, no one cared about. But today, people care about. And so we, sort of pyData ecosystem that have come after NumPy and pandas, inherit all these limitations. And though that affects us fairly strongly. So hardware has changed since 2001. We now have many cores. We have nice solid-state drives that are fast sort of extensions of memory. My laptop, this laptop is 4 cores. I think it has 4 gigabytes of RAM. I think 100 gigabyte hard drive. It's maybe 3 years old. And this is sort of the machine that I tend to target when I tend to build libraries. Old laptop. Another sort of interesting case is the sort of 32 or 64 core workstation, which is something fairly interesting. This is a picture of the Xeon Phi. So this is, I think, some 4 core, maybe it's an i5. This is a Xeon Phi. We're getting more cores, Moore's law, all that jazz. Problems have also changed, right? So NumPy was designed for scientific applications. Today we have larger data sets, we have messier data, we have missing values. We also have more text. We have JSON blobs and log files tend to be a big pain point today. And NumPy and Python are fairly terrible at these. So there's NumPy and there's pandas, and they have limitations. Below them, there's Python, which is even older and has more limitations. Notably, so it's sort of 1991. So think about what your computer looked like in 1991, or even if you were alive in 1991. And we didn't have many cores. We didn't have data sets like we have today. And so we have limitations from Python also. Notably, there's a thing called the global interpreter lock. Just so I get a sort of sense of the audience, who has heard of the global interpreter lock? Okay, I'm getting most people. Who fully groks the global interpreter lock and its limitations? There's a half a hand over there. Yeah, okay. So the GIL, it's often called, stops any 2 Python threads from manipulating Python objects at the same time. So you can still have threads, and they'll sort of trade back and forth as to who's running, but no 2 Python threads will actively change Python objects at the same time. And this sort of destroys Python parallelism. It allows for concurrency, but destroys parallelism, and that's a slight difference. So that's a pain if you want to use multiple cores in Python, right? Because suddenly we can't. There are 2 common solutions. One, we give up on threads and we use processes, which are a bit heavier. Sort of you have separate Python interpreters running. The main problem here is that they can't easily share data back and forth. The other common solution, and one that I think is really starting to take hold, even into in the last week, there's been a lot of progress here, is that the pyData ecosystem can just sort of skip the GIL, because we spend 99% of our time in C and Fortran code. We actually don't manipulate Python objects that often. If you're using sort of pandas or NumPy, you're sort of manipulating a Python object, but that Python object calls out to C or Fortran code. And if you're a little bit careful in designing NumPy and pandas and all these other libraries, you can say, oh, hey, wait, I'm going to skip into C or Fortran mode. I'm going to release the GIL, and then some other thread can do work while you're working in C and Fortran mode. So we have the opportunity in pyData, not in Python. Django is sort of screwed. But in pyData, we have the opportunity to skip this problem. And there's sort of some interesting work happening, not by me, by other people, happening right now. So that's sort of, I think, an interesting point. The GIL doesn't have to affect us. And we'll talk more about how that's useful in a bit. OK, so we have this problem that pyData rests on single-threaded foundations, both Python and NumPy and pandas. And that's fine. We've been very productive on top of those foundations, right? We've put hundreds of PhD theses into these boxes up top. And there's just amazing domain expertise here. So the color scheme here, projects that are the sort of reddish, orangish color hold the GIL. So Python, for example, holds the GIL. So it is hard to parallelize. Projects that are sort of this light blue color release the GIL. And so it is possible to write parallel code on top of them. So they're not parallel themselves, but it's possible to write parallel code. And so C and Fortran are possible to write parallel code. NumPy itself does release the GIL. So you can use NumPy in many threads, and it can be parallel. You can use 800% CPU resources. It's very nice. So if you're using NumPy and multiprocessing, wait, you don't have to. You can use threading. It's much faster. And then sort of above NumPy, there's a few projects, and some of them are blue, some of them are red. So notably, scikit-learn does release the GIL, pandas currently does not. And so it's interesting to sort of look at the map of all the projects out there and see which of them you could write parallel code on top of and which of them you could not. And there's other things. Theano is sort of special here because it is itself parallel. So the dark blue ones are parallel. So they're not only can you write parallel code on top of them, but they themselves write parallel code. So Theano uses GPUs, but it itself does not release the GIL. So if I want to use Theano multiple times, I have to use processes. So there's it's a little bit weird. So the question we really have here is, hey, we now have harder problems, we now have more cores, we would like to use all of those cores, but maintain all of the domain expertise and all of those PhD theses that are in the higher projects. So is it possible, right? Can we parallelize the ecosystem without touching all of the projects? Can we sort of flip a switch and suddenly have all of these projects be parallel because something underneath them is parallel? The answer is probably not. That's probably not going to happen. But it might not be hard. So we do need to touch every project, I think. There's some things we need to do, but it might not be hard to parallelize them. And sort of some of the work I do and other people around me also do is trying to do that. And we've tackled harder things. The pyData community is very strong. For example, I think most projects on this slide support both Python 2 and Python 3 simultaneously. And that's unheard of in the Python ecosystem, right? The core or the web teams don't effectively do that. So we have a very strong community. We have the ability to make some changes. The changes I'm talking about are releasing the GIL. So there's a pull request right now in Pandas where Jeff Reebok is slowly releasing the GIL. Scikit-image released the GIL last week. So there's some interesting things happening. And once we release the GIL, we then talk about parallel algorithms. Yes, question? How can I tell if a library releases the GIL? The question is, is there some way to tell if a library releases the GIL? One thing you could do is you could try to run two functions in that library in different threads and see if your CPU resources can go above 100%. If not, then it probably doesn't release the GIL. You can also ask. I highly recommend that everyone ask every project to release the GIL. That would be great. I've been applying pressure recently to projects, and it's been they're really responsive about it, but there does need some pressure from the community. Okay, so part of my work has been to parallelize not NumPy, but something that looks like NumPy. So there's a library called Dask array. And so this part of the talk will be sort of a general talk about a library that I think you should use or that I would like feedback on. So if you care about large multi-core arrays, this is maybe a sales pitch for a library. If you don't care about large multi-core arrays, this is an example of the kind of work that needs to be done to parallelize things. So we have a library that is already releasing the GIL. Now we want to write parallel code on top of that. And so there's sort of an example, again, of how to parallelize things. Just to give a real-world example of how you might parallelize a process, imagine that you're doing your laundry and you're folding all of your clothes. Okay? And suddenly 10 friends show up. And you say, oh, great, it's going to be 10 times faster. But actually, that's actually quite hard because everyone's reaching into the bag at the same time. They all have a different pile of clothes that they folded. It's sort of very hard to parallelize this problem. You need to maybe separate all of the socks and all of the shirts and all of the pants, and then give one to each friend. And so there's this extra administration that needs to happen with parallelism, sort of a recipe to follow, before you can effectively use all of your friends to help you parallelize some process. So we have the same problem with NumPy operations. So the sort of summary here is that Dask array is an out-of-core. When I say out-of-core, I mean that it works on data sets that are larger than memory by effectively using your hard drive. It's multi-core, meaning it uses all of your cores, n-dimensional array library. And in particular, it copies the NumPy interface for a subset of NumPy. So it looks and feels very much like NumPy, but works on larger data sets effectively. It does that using blocked algorithms, and we'll talk about what that means in a second, and task scheduling. And we'll talk about what that means too. Okay, there's related work. There's, in high-performance computing, there's big arrays. This tends to be more about linear algebra. In sort of data computing, there's things like Hadoop and Spark, which tend to sort of aim bigger than Dask arrays is aiming. We're not trying to replace Hadoop or Spark. There's task scheduling frameworks like Luigi, and then there's actually some closer peers like dist array from Enthod, Spartan, I think, at New York University, and Biggest at UK Met Office. If you care about previous work, you should go look at those. They're all great projects. If you don't, distinguishing features of Dask array. We're focusing on sort of n-dimensional array support, not just linear algebra. We're focusing on shared memory parallelism, so one machine, not a cluster, but just how we effectively use one machine. It's immediately usable. It's pip installable or conda installable. If you have Anaconda, it's probably on your computer right now, actually, without you asking for it. And there's also non-array things in there, which I'll get to later. Okay. So we're talking about blocked algorithms and task scheduling, and the NumPy interface. So let's break open the terminal here. So we have NumPy and Dask array. And NumPy, I assume people have used NumPy here, I'm going to assume. Or pandas, right? It's the same-ish thing. So there's NumPy, and here's Dask array. And there's sort of a similar set of functions in there. Doesn't copy everything, but a lot of things are there. Things like transpose and tensor dot and tangent, mean and sum and all that. So we can make some array, So let's make an array of normal random variables with mean 10 and standard deviation 0.1. Oh yeah, thank you. So let's, So this would work in NumPy, except that it's sort of a large array. NumPy could handle this, though. And we have to add one more keyword argument here, which is chunks. So this is a 10,000 by 10,000 array of normal random variables. And we're going to cut it up into a 10 by 10 grid, each size 1,000 by 1,000. So each of those chunks fit very comfortably in memory, even if the whole array does not. And we can do the standard things. About 100, and then take the mean, axis equals 0. And that's an array, and we're going to call compute on that. So if you're familiar with NumPy, that syntax should look very familiar to you. Sure. The podium, I see. Yeah, I'm not going to try to move that. Yeah. Perfect. So the idea here is that if you're sort of familiar with this line of syntax, should look very familiar to you if you use NumPy. And we just did an expensive thing, a hard thing, in a small amount of space, and only used a few megabytes of RAM. Yeah. So that's what I mean by when I say that it sort of copies the NumPy interface. Okay, so we did that with blocked algorithms, and we saw a little bit of that when we talked about chunks. We have a big array that we've sort of parceled out into many small NumPy arrays. So you can think of some sort of operations you might do, like let's find the sum of a trillion element array. So if I gave you an array with a trillion numbers in it, in some HDF5 file somewhere, so that's an 8 terabyte data set, and I asked you to sum all of them, how could you do that? Right. So one mechanism is you pull out a million-sized chunks. So pull out the first million numbers, take their sum, store that. Take the second million numbers, take their sum, store that. Do that 1 million times. Now you have a million small sums, and you do one more operation, which is this final sum over all of them. Okay. So that's what I mean by a blocked algorithm. We're using NumPy in memory, but it's on smaller blocks. And an operation like sum on the whole Dask array is just 1,000,001 smaller sums. Okay. This can get more complex. Like if you wanted to find the mean of all of the positive elements, you can't quite just take the mean of all the means, because they might be different sizes. So you need to take both the sum of all the chunks and the lengths of all the chunks, add up all of the sums, add up all the lengths, and then divide. And so these operations are sometimes very simple, like sum, and they're sometimes more complex, like the mean of the positive elements. Or you could think of, most people have seen blocked algorithms when they think about, if you're taking sort of a linear algebra course, blocked matrix multiply. So the most efficient way to multiply two matrices is to take them in different chunks and do small matrix multiplies. And the same algorithm for doing matrix multiply is actually, it looks exactly the same as for the blocked version. So Dask array does not just sums, but many other things that are sort of more complex. So this for loop is a problem because Python, the language, is going to do one step at a time. Do the first chunk and the second chunk. But actually, we could do these in any order, and we can do them also simultaneously. So this for loop isn't the right way to write this. We need to describe our computations in some other way. So Dask is going to describe those computations in this graph. And here's my favorite part of the talk, actually, where so I guess we should put. So I'm going to make a Dask array. So I'll make an array of ones. It's going to be this very small array. So it's 15 ones. And we're going to put that into blocks of size 5. And we're going to just visualize what that looks like. And we're going to start seeing these graphs. So these graphs, every circle is going to be a function, and every block is going to be a NumPy array. And so our whole array, this array of 15 ones, is composed of 3 small NumPy arrays, each of size 5, that were each produced by calling the functions ones. Okay, and this will make more sense in a second. So if I start to build up, if I do operations on my Dask array, my graph becomes more complex. So here, I make a bunch of ones, I add 1 to each of those blocks. I might then, take the sum of the whole array. Is this visible, people on the sides? Okay, sort of visible. I'm going to go for that. Control R, Control L? If this doesn't work, it's your fault. Yeah, I'm not too happy with that. Oh, you mean just to get more space? Or okay. Yeah. Let's just put this up here. That'll make it easier to read. Okay, so we write NumPy things and we get these graphs out. And I'm going to switch to a more complex array here, slightly more complex. So we get more complex graphs. And this is really nice because you get to see how these NumPy operations turn into blocked parallel algorithms. And so you can sort of watch the expression I type here on the right, like x plus 1 dot sum, and see the kind of operation it creates on the left. So when I did sum, we computed a sum of each of the chunks, took all those sums together, and did a final sum to get the result. So that's sort of what a reduction looks like. So making a 2-dimensional array, and we can do x plus 1. So this array is a 25 by 25 array cut up into 5 by 5 blocks. Sorry, a 15 by 15 array cut into 5 by 5 blocks. So there's 3 times 3. There's 9 different chunks. And if we do these sums, we see things like before. And if we do sort of more complex array operations, that array starts to break out in different ways. So we can do like, what would x plus x dot transpose look like? Think in your head what that's going to look like. And so here's what it looks like, right? And this is neat. You can see what different operations, So here is, for example, I think, a node like these three are on the diagonal because it's one block talking to itself. These nodes require crosstalk, and so they're the blocks off the diagonal. You can think about doing the matrix multiply. Yeah, just wait. And we can just keep going with this, right? The really nice thing about the NumPy abstraction is that we can keep creating these graphs completely, for as long as we like. Right? Yeah. Oh, nice. Okay. And so, sorry, I should also say we can keep as we do these NumPy, sort of the subset of NumPy operations, we can keep going ad nauseum. There are things that this can't do. There's no sort operation in Dask array because parallel sort's very hard. So there are definitely limitations, right? This is not all of NumPy. This is a subset, a surprisingly large subset that works quite nicely. So once you have that result, you call compute and you get an answer out. The input was a lot of ones, so the answer isn't very exciting. But when I called compute, 4 threads walked through this graph, executing all of these nodes in a way that was consistent with the graph, right? So we couldn't call this function before we had that data. And they did it in such a way that if the graph was relatively large, it would respect memory as much as possible. Sorry, question? Yeah, so the question is, can you then turn a Dask array into a NumPy array? The answer is absolutely. At that point, your whole array will be sort of brought into memory. So make sure that you do that after you do some other operations, but yes. So Dask array works, Dask array supports the dunder array protocol, and so it works anywhere that NumPy arrays are sort of expected. So I'll show an example in a second where we throw a Dask array into matplotlib functions, and matplotlib just works because it respects these protocols. Yeah. Okay, so let's switch back. Can I ask someone to give me some water? My throat's drying out, and it's not going to last another 25 minutes, and I've ran out of my water. Some wonderful person back there, I would appreciate that. Okay, so these graphs that we've just shown, we didn't specify how they were going to be executed. We just made this sort of recipe. But once we have this recipe, we can execute it, we can run it with multiple cores. Thank you, Philip. That was amazing. Cool. So to sort of show this, so we've seen these graphs before where the circles are functions, the blocks are NumPy arrays, and the flow sort of goes up. Okay. This is some embarrassingly parallel operation like x plus 1 times 2 to the power of 3. And so now we've added colors, and this is a trace of the scheduler running. Blue things are sort of free or released. So blue circles are done computing, and blue blocks, blue NumPy arrays, we've seen them, we've used them, we no longer need them, and we've released them from memory. Okay, so we're being very, very careful about the memory that we use. Red things are occupying resources. So the red circles are occupying a thread, they're currently computing, and the red blocks are in memory, they're resident in memory, they're filling up our space. And what you notice here is that the flow is going up. Right? So what we could have done is we could have run all of the bottom row of functions and had a bottom row of NumPy arrays all red. And that would have been bad, that would have filled up memory. Instead, we have sort of relatively cheap policies that ensure, to the extent possible, that we keep sort of only 4 red blocks at a time, as little memory as we can possibly hold. So the schedulers inside of Dask are very, very careful about managing resources. Another sort of point I wanted to really hammer home here is that we had this graph, and we just saw that graph being made in lots of crazy ways, and that was separate from the computation of that graph. That was a separate choice. Okay, so you could make your own function that executed these graphs, and you could still plug into all of the Dask array machinery, the creation of those graphs. Okay, so here's a fail case. I think this is x dot product with x transpose minus x dot mean. All right, it's 2 arrays. There's a fail case here. At some point, this whole row will be red. And that's fine. That just means we need to spill the disk, which we do effectively, but that does slow things down. You get to sort of the 100 megabyte. You're sort of limited by your disk bandwidth, 100 megabytes per second, something like that. Okay, so here's an example. So Dask array I need use cases for Dask array. So I asked all of my friends. A good friend was Stefan Hoyer, who works on X-Ray and works at Climate Corporation, and he's helping with some, we've helped each other build a nice sort of meteorological data problem set. Here is a year of weather data. So this is the temperature, 2 meters from the ground, everywhere on Earth, calculated every quarter degree of resolution. So every quarter degree latitude, every quarter degree of longitude, measured every 6 hours. These tend to be stored in netcdf files, which are a lot like HDF5 files, just sort of arrays on disk. So we look at one of these, and we see that it has the shape 4, 700, 1400. So that's 4 time measurements. 720 is latitude, 1400 is longitude, 180 times 4, 360 times 4. We have a bunch of those, so we're going to pull those into a list comprehension. So these are just netcdf data sets. They're sort of just like pointers to file the data on disk. They're not actually loading the data up. So we have all these different pointers. We're going to wrap each of those things as a Dask array. And as we do that, we tell Dask array how to grab data from that thing on disk. And Dask array works with anything that supports the NumPy get item syntax, NumPy slicing. And most things like H5Py or pytables or bcalls or netcdf all support that syntax. And then we're just great in NumPy land. We call concatenate, we get a large array, and we compute the mean and throw it into matplotlib. So this is the average temperature on the Earth for 2014. This data set, I think, is like 4 gigabytes or 5 gigabytes on disk. In memory, it's a bit bigger. It took a couple hundred megabytes and run on 4 cores to do this. Stefan Hoyer has data sets that are much bigger, 50 gigabyte data sets that he plays with on his laptop, which is very fun. And it's sort of the question before was, can I make this into a NumPy array? And no, sometimes you actually don't even have to, right? Because projects like Matplotlib will do that for you. If they don't receive a NumPy array, they'll try to turn it into a NumPy array. And Dask supports all the protocols to make that easy. Yeah, question?
I'm not sure if I understand it right, but you still have to take the things into memory right before you start working. So you cannot work with netcdf files directly, like one by one. You have to sort of pull all the data into your Dask arrays and then start to make something from them.
Right. So the question is, are you pulling all the data from disk into Dask arrays and then computing on them? Or is it something else? And it's something else. So that we don't pull all the data in at once. The bottom nodes of that graph are pull this section of this particular netcdf file into memory, then do some computation, and then release. And then another node is, okay, pull this particular other chunk from this other file into memory. And so I should also note that Dask array doesn't have an internal representation. There is no internal memory data structure of a Dask array. It's just this graph that pulls data from various places and has NumPy arrays in memory. So at no point is the entire array ever resident in memory. It's just sort of a recipe that will eventually materialize into the thing that you wanted. So, so we can do this on a terabyte data set if I had the disk space. Interestingly, I'm more limited by disk space now than RAM. That's actually what I care about far more these days, fast disk. Was there a question in the back? Yeah, so the question is, are we keeping track of intermediate results? Or do we recompute things? And so you'll notice that this is a directed acyclic graph and not a tree. And what do I mean by that? I mean that some of these values, like this value here, has many functions that depend on that value. And if you watch, when this goes red, it will not turn blue again until all of these have turned blue. So it's red now, and then boop, 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 now it's blue. And so we are keeping track of intermediate results, and we don't release data until it's safe to do so. Does that answer your question? So if I understand your question correctly, hey, I've computed this once, now I do something slightly different. Do I need to recompute everything again? So that would be great. I have sort of so one of the things that I do now is I build interesting schedulers that execute these graphs with different computational properties. And that would be interesting to do this sort of staging over time. You need to start thinking about caching rules. So no, there's not currently anything that does that well. You can compute multiple arrays simultaneously. If you compute the standard deviation and the sum at the same time, the sum comes for free because all the intermediate pieces are cheap. But no, that would be a very interesting thing to work on. Yeah. Okay, one more question? Yeah.
So in some cases you apply a function to basically is a one-to-one correspondence. And whether you do this in place or do a copy of an array. Let's say we're doing a logarithm of some intermediate result. Do this in place.
Yeah, so the question is, in cases like this, where we have maybe long linear chains of computations, do we need to have these intermediate results, or can you just fuse all of those together? And the answer is that we fuse. So there's some part of, Dask is, to a certain extent, a compiler that optimizes things. Okay, I thought I had, okay, yeah, well, I'm gonna skip all questions. Okay, so we've just seen that Dask array turns NumPy code into these graphs and executes them. But we can also think about not just arrays. There's things like bags or general lists of Python objects. There's things like data frames. There's also the custom code that you have. You don't need to think about these sort of big collections. You might just be able to write your own graph. I'm going to skip these, skip those. Quick note, Dask data frame is not ready for public use. People get very excited whenever I mention Dask data frame. Not ready yet. It does nice things for the projects that I work on it, but it's not robust enough. So we have these collections, things like Dask array, but there's more. They make these graphs, and then there's schedulers. The nice, robust schedulers are all for single machine parallelism. I have a experimental distributed memory scheduler, which could execute those graphs distributed machine, but that's also not quite ready. But these two sides don't need to know about each other, right? So you could make your own collection and make a task that makes task graphs, just Python functions that make these graphs, and then execute them. So I think that there's actually this is an avenue I'd like to explore in the near future of forget the collections entirely and just think about Dask graphs and the Dask schedulers as being nice mechanisms to parallelize other libraries. So what is a Dask graph? So this is the simplest mechanism I could find to define a Dask graph, or a graph of a directed acyclic graph of task dependencies. A Dask graph is just a dictionary where tasks are tuples, the first element of which is a Python function, and the rest are either data or other keys in the dictionary. So what does that mean? Consider this computation where I have two functions, just normal Python functions, increment and add. I set x to 1. I set y to the result of inc called on x. I set z to the result of add called on y and 10. Okay, so it's a very simple computation. In Dask, you would represent that as this dictionary. Okay, so I did this sort of weird thing where, can people see this far down? Is that, no? Thank you for saying. Yeah. Nope. Okay, so that's as good as I can get, and I apologize. So it's a dictionary, done this weird thing where a function call is delayed by moving the parenthesis from the right side, because we don't want to call it yet. We want to store it as a data structure over to the left. Lisp developers will be very happy with this. Everyone else will think it's kind of weird. But that's the internal representation of a Dask graph. And so if you can make that dictionary, you can use any of the task schedulers. You actually don't even need to import Dask at this stage. So here's an example using array. So we saw this example before with NumPy arrays or with Dask arrays. And a Dask array has a Dask attribute, which is just this dictionary. So if I call a range, just make the numbers 0 to 15, Dask just splits it up as 3 separate calls to the NumPy a range function. And as we do more complex things, that dictionary becomes larger. You can imagine having your own pipeline with your own functions in there and making your own graphs. And then calling, I'm not going to resize it, but there's a very simple interface to call the schedulers on that. Okay, so you can use the schedulers without the arrays. This is going to be my last bit. So scikit-image, as of a week ago, now depends on Dask array. We're actually their second dependency after NumPy. We were very, very proud. And there's a sort of interesting story that happened. So we have a mechanism to parallelize slightly overlapping regions, which works very well with scikit-image functions, which need to sort of think about very local operations, windowed operations. So Blake Griffith, a Dask developer who also works Continuum, in sort of part-time work, sort of integrated the two. We found it wasn't very fast because scikit-image didn't release the GIL. Johannes Schoenberger and Stefan Vandervolt released the GIL in Dask array, or in scikit-image. Oops, that's not what I wanted. I wanted that. And this pull request is actually really slick. This is what it costs to release the GIL. You need to think a little bit about your code, but it mostly means adding no-GIL tags and no-GIL with blocks. This is not hard to do, and some tests. The longest thing is the tests. And they also thought a lot about where it was safe to do this. And now you can use them together to get sort of 2 to 3x speedups. And that was cheap. Okay. Jeffrey Bach this morning said, so Jeffrey Bach is now slowly releasing the GIL in pandas. Okay. That's it. Thank you all for your time. I probably don't have time for questions, but please talk to me afterwards.
Thank you very much, Matthew. It was a great talk. We maybe do have time for one last quick question.
Oh, perfect.
The big achievement of NumPy was to unify communities, so to have one array representation. And now you have Bigus and Spartan and Dask. So are you guys talk to each other, or we again in this stage where we split community a little bit in this sense?
Yeah, that's a great question. So we all talk to each other socially. I don't think we've talked seriously about the different projects. I would say, so Distarray, you also forgot, is also a good project. I don't know the development status of Spartan. I think the main developer sort of left, and there's a couple of people now working on it. It's mostly academic. I've reached out to them, I haven't gotten much back. I haven't talked to the Distarray people recently, but there's maybe overlap there. Blake Griffith, actually notably, used to work on Distarray. And I'm talking to the biggest guys next week. I'm usually in California. I'm in Europe for a bit, so I'm going to go talk to them. There's not as much conversation as I would like to have, but it's also okay. It's an experimental field. I would also suggest that there's also a lot of excellent task scheduling frameworks. That's also a sort of open opportunity for more conversation that also isn't happening. So you talked about arrays, but also task scheduling is a big open space. All of us also support the NumPy, the array protocol. I think it is okay to have disparate projects as long as you adhere to some protocols. And NumPy did do a good job at standardizing that. So I think maybe now is a good time for experimentation. Yeah. Okay. Thank you.